and the image frequency, and what is the importance of image frequency rejection. Okay, yeah, yeah. So to start with, there is this RF section. Uh, so I hope I haven't talked about RF section, like RF amplifier and such things. Yeah. So let me quickly start with that, and then we'll go to sensitivity, selectivity, and image frequency in this class. So yeah. So in today's class, we'll be dealing with different aspects or sections or sections of super heterodyne receiver. Super heterodyne. So if you go and see your block diagram, the block diagram we have drawn about super heterodyne receiver, you will see the first block is RF stage, right? So this RF stage may or okay, the RF stage is nothing but the antenna coupling circuit. So there is an antenna, right? So from this antenna there is a coupling circuit. See, this antenna receives all the frequencies in the AM band. This antenna is designed such that it receives from 540 kilohertz to 1640 kilohertz. But when we right, so this coupling, but when we tune our radio to a particular frequency to listen to a particular radio station, we tune this coupling circuit to that particular station so that only those frequencies get passed into this. So an RF stage, in every radio receiver, RF stage essentially contains this antenna coupling circuit. So this is called antenna coupling circuit, and RF stage may may also contain may also have an RF amplifier, right? So what I'm saying is that in general it can be this antenna coupling circuit plus RF amplifier. So but not all the receivers may have this RF amplifier. In very good receivers, like in high sensitivity and high selectivity receivers or costly receivers, you will definitely have this RF amplifier. And in some of the simple receivers which are of low cost, and mainly those which can be used in urban scenarios, need not have this. So this may or may not be there. So what is the necessity of the RF amplifier? RF amplifier provides further gain to the incoming signal, so your quality of reception gets increased, and also it increases the selectivity of the receiver. So let me, yeah, so let me come to this. So having RF amplifier is better, but it also increases the cost of the receiver. Is better from sensitivity. So we will define these terms: sensitivity and selectivity viewpoints. Sorry. Say so that's what I'm saying. If you are living in a urban scenario, say there is a Vijayawada All India radio station, and if you are living in proper Vijayawada, like in the city, not in the outskirts, like not in the outskirts of the city, then you will have enough signal strength. So you don't need to have an RF amplifier exactly. So a receiver without an RF amplifier will also work well in such a case. So it all depends on your application also. If you need a very high quality receiver, you need to have an RF amplifier. So as I said, it amplifies the incoming signal. So even if you receive a weak signal, you will be able to listen to the radio programs with much more clarity. So that covers the sensitivity. Sensitivity is even for small incoming received signal amplitudes, even if the input signal amplitude is very low, you will be able to decode it, you will be able to demodulate it and listen in a better manner. So what about this selectivity? So now think about the selectivity. So selectivity is the uh, the particular station that we want to select, the frequency selectivity. What I mean by selectivity is the frequency selectivity. Okay, so when we talk about selectivity, RF amplifier. So input to the RF amplifier is from the antenna coupling circuit, right? So this antenna coupling circuit, which is a tuned circuit, RL or RC or RLC circuit, right? So this already has got a bandwidth centered around the carrier frequency. Say if we want 660 kilohertz, then it a radio station centered with a radio station with its carrier frequency is 660 kilohertz. Then we'll tune this coupling circuit to 660 kilohertz and with a bandwidth of 10 kilohertz. Then it already filters, but so that signal goes to RF amplifier. RF amplifier again amplifies the signal, but at the output of the RF amplifier there is another tuned circuit. That tuned circuit is once again ensures that the signal output from the RF amplifier is within the required bandwidth. We'll have a tuned circuit at its output, and it also ensures, sorry, spelling mistake. And it also ensures that only the wanted frequencies means the desired radio station, only the wanted frequencies are allowed or passed, and the unwanted frequencies are blocked, right? So if we have an RF amplifier, it has got two advantages. One is it amplifies the weak signal into a larger amplitude, and thus it provides a better quality of output in terms of audio power or volume or whatever. So in such a case, even if you have a very weak incoming signal, even if you are very far away from the radio station, radio transmitter, you can still able to get a very good quality output from your radio. So that's one thing, that's the sensitivity. But it also helps you to reject unwanted frequencies. So if you tune to a particular station, only that particular station you will receive, but others, the adjacent stations. So in frequency spectrum, there may be one radio station at 660 and another radio station next to it, and before that there could be another radio station. So RF amplifier will have one more tuned circuit. It has one more tuned circuit, and initially we have one tuned circuit here at the output of the antennas. So having two tuned circuits, so tuned circuit is nothing but a band pass filter, right? It acts as a band pass filter. So having two band pass filter, even if some signal escapes, even if there is some unwanted signal that is not filtered by this initial tuned circuit, or which escapes this initial tuned circuit, then there is another tuned circuit offered by the RF amplifier, and so your selectivity like increases. Like you won't pass any undesired signals into the mixer input. So this is the necessity or the functionality of RF amplifier. Okay, and as I said, RF amplifier is not strictly required in all the cases, but if you have it, it's better. If you have RF amplifier, your receiver will have higher sensitivity and higher selectivity, but also the cost of the receiver also increases, right? So yeah, so this is about RF amplifier. Next we will go to the next section. If you see, it is a mixer, and then so before discussing all those things, we will discuss what is sensitivity and what is selectivity in more detailed manner. Right, so we'll discuss about this sensitivity first, and then we'll discuss about selectivity. So sensitivity is a measure of it's a measure of the ability of the receiver to amplify weak signals, to amplify weak incoming signals. So we say that my receiver is very sensitive. It can also pick up that distant radio station. It works even when the weather is bad, right? These are the times. If you, of course, nowadays nobody, you rarely see people using radio, but if you talk to your elders, or if you go to some villages, maybe still they will be listening to radios. So they keep mentioning about such things. This radio is very good. It works even with a very weak signal and so on, right? Such radios are called to be having very high sensitivity. So this sensitivity there is a standard way of measuring the sensitivity. Being engineers, we should quantify. See, always the science and engineering, what it does is it won't leave the words ambiguously. So if I say my sensitivity of my receiver is high or low, medium, we, we we have to quantify those words. Like we have to give a number to those words. What do you mean by high? What do you mean by low? What do you mean by medium? Right? So to avoid these things, we'll measure this sensitivity in the following way. So what happens? How do we measure sensitivity is, so they defined one of the standard ways of measuring sensitivity. So a carrier is modulated, a carrier in between. So we are talking about AM range, right? So 540 kilohertz. If it is if it is AM receiver, then how the sensitivity is measured? We take a carrier, and that carrier should be within 540 kilohertz to 1640 kilohertz in case of amplitude modulation. So carrier is 30% modulated. So we know the percentage of modulation formula, right? There is in while discussing AM, we discussed what is the percentage of modulation. While discussing FM, we discussed what is the percentage of. So carrier is 30% modulated by a sinusoid at 400 hertz, I guess. Yeah, at 400 hertz. Yeah. So here the baseband signal is 400 hertz sinusoid, and using this m of t. So what do I mean to say is m of t is 400 hertz sinusoid, and it is used to modulate a carrier, and the percentage modulation maintained is 30%. So this is step 1. So step 2 is the modulated carrier is applied to the receiver, is applied to the input of the receiver, through a standard coupling circuit. See, we will avoid the and in measuring the sensitivity. So there is a receiver with us, right? So that receiver we will directly give it to through some standard coupling receiver, through some standard coupling circuit, like through. So our purpose is not to test selectivity at this point, right? It is only the sensitivity through a standard coupling circuit. Through a standard coupling circuit or network, it is more common to call it as network, known as dummy network. So we have given this input through some dummy network to the input of the receiver, and then we will measure the output of the receiver. So generally, what is the output of a AM receiver? It's voice. It's some audio signal, right? So here what we do is we don't see audio signal again. You cannot measure the quality of the audio signal. If the same audio is listened by two different persons, somebody may say the quality is good, the sound level is good and all, but somebody else may say no, it's noisy and it's not as good as I expected. So we again quantify that. So we remove the loudspeaker, we replace the loudspeaker with an equivalent resistor, and we will find the output voltage or power of the receiver, right? Because output voltage can be measured in terms of how many volts we are getting, and output power can be measured. What is the how many watts of power we are getting at the output of the receiver, right? So we will replace. So replace loudspeaker with a load resistance of resistor of equal value. Say the loudspeaker will also have an input impedance, right? In input resistance. So we'll replace it with a load resistor of equal value. So okay, so we have applied input through a dummy circuit. We have applied a 30% modulated signal at with modulating signal is 400 Hz sinusoid, and then we replace the output loudspeaker with a load resistor, and then we will look for 50 milliwatt of power. So at the output we will connect a power meter and we will try to measure the power measuring the sensitivity. So you apply the input signal, you modulate, you generate a modulated signal, apply that signal through a dummy network to the input of the receiver, and then at the output replace the loudspeaker with a load resistor of equal value. So we have removed the loudspeaker and connected a load resistor, and then what I was saying is increase the input signal amplitude gradually and look for an output power of 50 milli. Sorry. And look for an output power of So the input voltage required to produce output power of 50 milliwatt is the sensitivity of the receiver. Right? Say for example, it is something like this. The receiver, the sensitivity of this receiver is 12.7 microvolts or 10 microvolts for an output power of minimum 50 milliwatt. So this voltage is expressed in volts. What do I mean by volts is it can be millivolts, it can be microvolts, or it can be volts, right? Expressed in volts, or it is also expressed in dB volts. So measured in decibels below or decibels below say for example the sensitivity can be 12.7 microvolts. So this example I have taken from the textbook, the Kennedy textbook. So 12.7 microvolts, and how much it is lower than 1 volt. So it is when you convert that into, so or this is equivalently minus 98 dB volt. So how do you compute dB volt? So you compute like this: decibels below 1 volt. So this 12.7 microvolt is below 1 volt, right? And how much it is below? That is minus 98 dB, right? So you know about dB milliwatts, right? You know dB you know dB milliwatts. So how do you measure dB milliwatts? How much it is below? Yeah, just a minute. This pen is creating. Yeah. So similarly, it is measured also in dB millivolt. So if somebody gives you the sensitivity in dB volts, then you can convert that into volts, or if they have given you this, you can convert that into this, right? So yeah, and sometimes what some receivers, some professional receivers, like they also give you that the receiver sensitivity is some 15 microvolts or 10 microvolts or 13 microvolts uh, for an output power of 50 milliwatt and at an SNR of something like 20 dB, right? So some receivers also mention the output SNR. So I'll tell you what is SNR. The output SNR along with the output power. So we haven't studied noise. So noise, you will understand this term better. So SNR is signal power, the ratio of signal power to noise power. So this is called signal to noise ratio. Signal to noise ratio is SNR. So if the signal to noise ratio is high, that means the noise is low, the signal is high. So you will get a much better output. Like you won't get any noisy output. There won't be any humming sounds or noisy sounds in the audio quality, right? If the SNR is low, you will get a, see, if I fix only, if I consider only my output power, right? See, this is slightly troublesome in some cases, because say I have a receiver which requires 10 microvolts to give me an output power of 50 milliwatt. So I have a receiver which requires only 10 microvolts to give me an output power of 50 milliwatt. So we call that receiver as having sensitivity of 10 millivolt, 10 millivolt. But if I but the signal to noise ratio at the output of that receiver may be only 10 dB, right? So maybe the noise is only 10 dB lower than the signal power. Microvolt of input amplitude to give an output power of 50 milliwatt, same as the first receiver, but its output SNR, signal to noise ratio, if it is 20 dB, right? 20 dB meaning at the output of the second receiver, the signal is 20 dB higher, 20 dB above the noise level. So that output quality is much better than the first receiver's output quality. So we should accept the second receiver as the better receiver, right? So what I'm trying to say is that there are two receivers. So sometimes the sensitivity is mentioned by stating both the output power and the SNR, right? So something example is something like this. for a minimum output power, power of 50 milliwatt at a minimum SNR of 20 dB. This receiver, see, you may find such a specification on the receiver data sheet. If you go and buy a receiver, or if you go and see some of the data sheets of these receivers, this receiver requires say 10 microvolts or so many dB volts. So this may be example of one receiver. So there may be another receiver which also says the same, for a minimum output power of 50 milliwatt at a minimum SNR of at a minimum SNR of 10 dB. This receiver requires 10 microvolts. Then you should. That's what I'm trying to say. So the higher the SNR, the better the quality. Better the quality of the output signal. So if I have a high SNR receiver, I'll receive a high quality signal I will listen a high quality signal at the output of the receiver, right? So now another important thing is this measured. Okay, let me not write the entire sentences, it is taking a lot of time. So the sensitivity is measured along 3 points in the measured at 3 points at least. At 3 points over the frequency range. Over the frequency range of interest. So what I'm saying is that if the receiver is supposed to operate from 540 kilohertz to 1640 kilohertz, we will measure at least 3 points in this spectrum. Maybe one at 600 kilohertz, another is maybe 1100 kilohertz, and another is at maybe 1500 kilohertz. So at least 3 points the sensitivity will be measured, right? And let me show you a typical curve of a sensitivity curve. So it is something like this. A typical sensitivity curve. Okay, what is this? So it is something like this. So this is frequency and this is sensitivity. Sensitivity in say maybe microvolts. Okay, the units along y-axis is microvolts, and this is frequency, and say this is the 500 kilohertz. So we are starting not from 0 but at 500 kilohertz, and then they say maybe this is 1700 kilohertz. So we are measuring the sensitivity from 500 kilohertz to 1700 kilohertz. Then this is one example of a sensitivity of one particular receiver. So if you take a receiver and measure its sensitivity over the entire frequency range, or the entire frequency range from 500 kilohertz to 1700 kilohertz, and then you may you may get a response. So I'm not saying all the receivers will have the same response. So this may be one particular receiver's response, right? Say this may be, yeah, this may be 10 microvolts, maybe 11, 12, 13, 14, and so on, 15. Right. So what does this mean? At 500 kilohertz, it needs at least 12 microvolts. At 500 kilohertz, it needs at least 12 microvolts to give you an output power of 50 milliwatt. So its sensitivity is 12 microvolts, but its sensitivity is good in the sense it needs, sorry, yeah, it needs only maybe 10.5 microvolts here, right, at this frequency. But at this frequency, it needs 15 microvolts or maybe 20 microvolts. So this is a typical sensitivity curve of a receiver. So what I was saying in the RF, when I discussed at the beginning of the class, I discussed this RF amplifier, right? So if I have a RF amplifier, this sensitivity will, like, so even with very low input voltage, you will be able to operate. So that's it. So yeah, so this completes our sensitivity discussion. So this one example curve. Maybe you will do one experiment in the lab. I don't know about your lab course, but yeah, you can measure the sensitivity. It's not a, so what you do, you take a 400 hertz sinusoid, you modulate it with one carrier frequency, maybe 600 or 700 and so on, and you modulate it at 30%, and then keep increasing the input voltage, and then measure the output power. Right. So next we will discuss selectivity. Right. What is selectivity? So anything else? Okay. Yeah. So selectivity is a measure of so selectivity is nothing but ability to reject unwanted frequencies. And so we'll similarly see how do we measure it. So the measurement process is very similar to what we did in measuring the sensitivity, and also it is expressed as a curve. So it is as a plot. So let us see one such plot, right? So it's something like this. You have a receiver, you tune to a particular frequency, maybe 660 kilohertz or 700 kilohertz. So you tuned it to a particular frequency. So let's take that to be 700 kilohertz, right? And when you apply a 700 kilohertz input frequency, the receiver will give some output, right? The receiver will give some this many volts as output and this many milliwatts as output. Now vary the input frequency. So don't change the tuning of the receiver. So the receiver is tuned to 700 kilohertz only, but the input frequency you increase from 700 to maybe 1600, and then decrease from 700 to maybe 500, right? Or like so if you change the input frequency, obviously the output signal will reduce. The receiver, because we have tuned to a particular frequency 700 kilohertz, but the input frequency is not 700 kilohertz, it is 690 kilohertz or 680 or 660 or whatever, and or it is 710 kilohertz or 720 kilohertz or 730 kilohertz or whatever. So when you are changing the input frequency, the output amplitude, either the output, both output power of the receiver and output voltage of the receiver decreases. So how much it decreases, you note down, and that tells you how selective your receiver is. So I'll write this down, whatever I expressed in orally. So a typical selectivity curve will be something like this, right? So it is say this is 20 dB. I'll tell you what are these things. 40 dB, maybe 60 dB and 80 dB and so on. And say this is 0. So this is 0. So maybe it is 20 kilohertz. So it is 10 kilohertz. It is 10K. Again 20K and so on. So this is not exactly F. So you can call it as delta F. Say for example, I have tuned my receiver. So okay, let me write down the entire procedure. Then we will understand this. So this is the attenuation. This axis is. So how do we measure? So measurement procedure is something like this. So again, take a carrier frequency . and modulate it with 400 Hz sinusoid at 30% modulation. So this carrier frequency, maybe let's call this as FC. Okay, so we have taken a carrier frequency FC and then modulated it with a 400 Hz sinusoid, and the percentage modulation we kept it at 30% percentage modulation, right? Then same, apply this signal to the input, apply this modulated signal to the receiver input, through a dummy network. So the process is same as that, but except here we change the frequency. Replace the loudspeaker with an equivalent load resistor. Right? Okay. So you have applied the input frequency FC, you measured the output signal. Okay. Measure voltage at a fixed input voltage. Okay, here comes the difference. In case of sensitivity, we kept on increasing the input voltage and observed when we will get the 50 milliwatt output power, right? So here that's not the case. You keep the input voltage fixed at some voltage, right? At some voltage, maybe preferably at the range of its sensitivity, and then measure the output voltage. Okay, so you applied a carrier signal modulated, a carrier signal at FC, modulated signal, and then kept the input voltage constant and measured the output voltage. Note down that. And then if you now vary the FC, vary this carrier frequency, and don't vary the input signal amplitude. So obviously your receiver is tuned to FC, signal to the receiver input through a dummy network. Here I forgot to say, make sure that you have tuned the receiver to FC. So we have tuned the receiver to FC and applied the signal. You get a output voltage. So take the ratio of okay, you get, and then now you are keeping, you are varying the input amplitude. You are varying the input amplitude. Sorry, input frequency. Yeah, I should not be saying input amplitude. Now keep varying the input frequency by keeping the input amplitude fixed, and note down the output amplitude. And then how do you do this? Is take the ratio. So when we vary the input frequency, above FC. The output voltage falls, right? Output voltage decreases. Yeah, maybe that's a better word. Now instead of FC, that means you change the input frequency to FC plus 10 kilohertz. Okay, so the output falls from the previous output value. Now you increase the input voltage to again get back the old output voltage, right? Say for example at FC, output voltage is V naught for an input voltage of Vi. Right, now change the input frequency. Now change the frequency to FC plus 10 kilohertz. The output voltage falls to a low value V naught prime. So the output voltage falls to a low value which is V naught prime. Okay, so increase input voltage from Vi to Vi prime to increase the output voltage from V naught prime to V naught. So previously we had an output voltage of V naught, right? Now as I changed the frequency, the output voltage has decreased from V naught to V naught prime. So what I am saying is that now increase the input voltage from Vi to a new value Vi prime, so that the output voltage will again increase and reaches the previous output voltage which is V naught. And then now take the ratio Vi prime divided by Vi and express it in decibels, right? So now how do you plot this curve is at 10 kilohertz, at Fc plus 10 kilohertz, your attenuation is 10 log 10 Vi prime divided by Vi, right? So 10 log to the base 10 Vi prime divided by Vi is the attenuation offered by the receiver, attenuation at Fc plus 10 kilohertz. Right? So that means at 10 kilohertz, if I get that 10 log 10 Vi prime divided by Vi is equal to 20, this will be that value. Right? So you please make a note of it. I'll take just like just 1 minute break. I'll mute my. Now the y-axis point is 10 log 10 Vi prime by Vi. Right? So this is how you generate a sensitivity, a selectivity curve if you are asked to do so in a laboratory. Right? So let's go back to this curve and then see. So what does this mean? Signal at Fc. To get the same amplification is transmitting at 60 dB more. So in general, what happens is we know that there is this incoming signal frequency and there is a local oscillator. So the incoming signal oscillator and the local oscillator frequency, they are mixed in the mixer, and the mixer output frequency will have the sum component and the difference component. Say the incoming frequency is Fs. So this is the incoming frequency, incoming signal frequency. And Fi, Fo. Fo is the frequency of the local oscillator signal. Frequency of the local oscillator, and let Fi is the intermediate frequency. Which is 455 kilohertz. Right? So when this Fs and Fs and Fo are given to the mixer output will have Fo minus Fs, Fo plus Fs, and Fo and Fs. So generally Fo is maintained higher than Fs, higher than the incoming frequency Fs. So that implies if you tune your receiver to Fs, then the local oscillator will be tuned to Fs plus Fi. So if you if you tune, say if you tune your receiver to 700 kilohertz incoming signal, say if you want to receive a radio station at 700 kilohertz, then your local oscillator will be tuned to 700 plus 455 kilohertz. So which is 1155 kilohertz, and then this 1155 kilohertz of local oscillator signal and 700 kilohertz of incoming signal are both given to the mixer, and the mixer output will be F0 minus Fs and F0 plus Fs and F0 plus F0 and Fs. So in that the IF stage amplifier, the IF amplifier will select only the 455 kilohertz signal, right? So that's how it works. So let's write these equations here. So we have F naught is equal to Fs plus Fi, or in other words, your Fs is equal to F naught minus Fi. Fi is IF frequency, right? Okay. Now assume that an input signal at frequency, assume that a signal at frequency Fsi, right? So this here the I refers to image frequency, so that we will discuss later. But at frequency Fsi is equal to F naught plus Fi, or in other words, this is Fs plus 2Fi. See, when I say this, this is another incoming signal. This is another signal at some frequency Fsi, and that frequency happens to be exactly same as F naught plus Fi. But we know that F naught is Fs plus Fi. F naught is Fs plus Fi. So this Fsi can also be written as Fs plus 2Fi. So if a signal at this frequency, now assume that a signal at frequency Fsi reached, okay, let's assume that it somehow reached the input of the mixer, reached the input of the mixer. Then at the output of the mixer, so as I said, the mixer will have the sum and difference frequencies of Fsi and Fo, right? So we'll have one difference frequency which is Fsi minus Fo, so which is equivalent to F naught plus Fi, because Fsi is equal to F naught plus Fi, right? Minus F naught, which is equal to Fi, right? So at the output of the mixer, we'll have Fsi, we'll have another IF frequency, but this IF frequency corresponds to the incoming frequency at Fsi, not the incoming frequency at Fs. Now assume that this Fsi is another radio station signal. So let's assume that Fsi is a carrier signal corresponding to another radio station, and then that happens to somehow reach to the input of the mixer. Okay, we know I know that we have tuned only to the signal, the antenna coupling circuit is tuned only to the signal Fs, right? So at Fs, but somehow due to some imperfections in our input selection circuit, another signal at Fsi also reached, another radio station operating at Fsi, it has also reached the input of the mixer. Then the output of the mixer will have IF frequency, and that IF frequency corresponds to the radio transmission at Fs as well as to the radio station at Fsi. So that means we will be listening to two radio stations simultaneously, and both the signals get mixed, and then you will listen. It's a kind of noisy signal. So when it's the effect is similar to like two people are talking to you simultaneously. See, if two people are talking to you simultaneously, then you don't listen to you cannot make out of anyone's voice. So such a phenomena happens, and this frequency FSI is called the image frequency. So FSI, which is equivalent to, say, when we tune to a signal Fs, we are also able to listen to a signal which is Fs plus 2Fi, and this new signal FSI is called the image frequency. Yeah, so this I need not write it actually again. So FSI image frequency of Fs. The signal at FSI is called the image of the signal at Fs. Like it has got, like we can listen to another spurious signal. So if there is only one tuned circuit at the input of the, okay, now we said that the RF stage, the very first stage of the super heterodyne receiver, may or may not have RF amplifier, right? So we said that there is an antenna and there is an antenna coupling circuit, and now assume that if there is no RF amplifier in the RF stage, so then there will be only one tuned circuit, which is the antenna coupling circuit. So the how much that coupling circuit rejects this image frequency is given by the following formula. So the ratio for a single tuned circuit the ratio of the gain at frequency Fs the ratio of the gain at Fs to the gain at FSI. That means what I am saying is gain at Fs divided by gain at FSI is given by alpha, and that alpha is 1 plus q square rho square, where q is the loaded Q of the tuned circuit, and rho is defined as FSI divided by Fs minus Fs divided by Fsn. So this is the formula. So if alpha is very high, what does that mean? If alpha is very high, gain at Fs is very high compared to gain at Fsi, and we are able to reject the image frequency in a better way. So alpha is called the image frequency rejection ratio, right? Yeah. If alpha is high, that's a good thing, and think about it. When alpha is high, for alpha is high, when Q is high, and also when a rho is high, right? So Q depends on the tuned circuit, the Q factor of the tuned circuit, right? And rho depends on what? See, the rho is the image frequency divided by signal frequency minus signal frequency divided by image frequency. So if FSI is very high compared to Fs, so what I'm trying to say is rho is high when FSI is much higher than Fs, right? Because you can see that when FSI is very high, then this will be very high and this will be very low, and then rho will be high, right? So what does this mean? We know that FSI is, so FSI much higher than Fs means Fs plus 2Fi is much higher than Fs, right? I can cancel this both sides, so that implies Fi should be very high compared to 0. So if our IF frequency, this implies if the IF frequency, intermediate frequency, the IF itself means intermediate frequency. If the IF we get a better, we get a higher alpha, and thus can reject the image in a better manner, right? So I'll stop here for today, and then we'll solve 2 example problems in the next class.